Good afternoon, this is Mr. Couple. Today I'm doing a lesson for my IBSL Year 1 students. We'll be doing some ideal gas investigations. Once again, I'm all alone by myself here. I'm just gonna cry. Nobody wants to come to my live streams. But at least you guys are watching them on YouTube and completing the lessons. I do appreciate all of your efforts for completing these assignments. You guys are awesome. Thank you for everything. If you have questions, just come on by, office hours or live stream. I'm glad to help you guys out. All right, so the lesson for today is not like the other ones. We're actually doing a quasi experiment today. So I posted the assignment on Google Classroom. You're going to want to pull up this Google Doc and you're going to want to pull up this ideal gas simulation on FET. The Google Doc is just going to take you through some instructions on what you're going to want to do and things like that. Let me zoom in so you can see a little bit better. Yeah, that looks pretty good. All right, so basically, we're going to be investigating an ideal gas. The goal is to discover the gas laws. There are four of them that you'll be investigating today. I'm just going to walk you guys through the first one and how I did it, and I'll show you sort of an example of what that looks like. And then you are going to go on your own and finish the remaining three. We're not looking for like this isn't a lab report or like a formal lab. We're just going to try to keep things simple and just sort of establish the basic idea and concepts behind modeling a gas. Like we're trying to figure out how the particles in a gas behave and like bounce around and collide with each other, looking at it from the Boltzmann equation idea, like the average kinetic energy is directly proportional to temperature and things like that. This is the second half of the thermal physics unit. I also have symbol salad open just in case I need to, grab any Greek letters to paste into the spreadsheet or anything like that, like superscript, subscripts, things like that. Okay, so what we're going to want to do is when we pull up the simulator, we're going to want to go to the ideal gas simulation, and we're going to want to do a few things. So let me show you. It's all in the directions here. So the simulation looks like this. So that's what we saw. Turn on width display and make sure the temperature and pressure are in SI units. So we'll go back here. So we're going to turn on the width display. Bloop, right there. Now we can see the width. We're going to need some quantitative measurements here. So it's important to be able to read off the data. And I also said make sure everything's in SI, so that's Kelvin and Pascal. So the Pascal, I haven't taught you guys about pressure yet. I wanted to do the simulation first, and then when I actually go and teach the concepts, I think they'll make more sense because you'll have played around in the simulation. And you sort of have an idea of what's going on more readily there. The other thing that I'd strongly recommend doing, it's not required, but we're going to kind of hack the simulation. So if you go into options, you can turn off the pressure noise. What will happen is when the particles, so if we inject some particles into this container, the particles will start bouncing around and like they're randomly moving and like bong, 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 kind of like, pinball, like they're bouncing all over the place or pachinko, if you know what that is. And they're going to, every time a particle collides with the wall of the container, the particle exerts a force on the container. Now it's these massive amounts of all these particles bouncing all across the container repeatedly, and that's what gives rise to the pressure. So when we cheat and we turn off the pressure noise, when we turn that off, you can see when the pressure noise is on, there's a bit of variation there in the pressure. And we just want to turn it off. So we'll tell the program, hey, you know what, just give me an average, like just cancel out the noise. This is just going to make it much easier for us to collect data. When we do the actual experiment, we will leave that random noise on because it's more realistic to what it would be like in real life. But just for this introductory experiment, we'll leave the pressure noise turned off. Okay, next. So what we're going to do is we want to add 500 heavy particles to the simulation. So if you look down here, I've got 300 right now. So that was just from like these random pumping. So it looks like every time I pump, I get about 50. So I'll just go to 500. So 500 is good. And we'll just let it kind of mix in there. Give it enough time for all that energy to sort of randomly disperse around and even out. The simulation is ready. So now it should look like this. Let's just check to make sure it looks like that. We're good to go. All right, so here I gave you some notes on simplifications that the model, because obviously these aren't real gas particles, but you will notice that this is 10 nanometers. So you got this really teeny tiny box. It's only 10 nanometers wide. And so it is trying to do its best to appropriately mathematically model and simulate what the particles of a gas actually look like and how they behave within a cylinder or a container that's this small. So here are some simplifications that this model makes. I don't think I'm going to go into too much detail here, but basically the particle collisions are modeled as hard sphere collisions. So that way the particles can be elastic. So they'll hit and then just transfer kinetic energy and conserve momentum. The container depth and height are constant, so volume varies linearly with width. We are going to need to know that. So over here in my spreadsheet, I'm going to make sure that I write that down. So the depth is 4e negative 9, 4 capital E negative 9. And so that's going to give me nanometers. That's what the E negative 9 is. It's times 10 to the negative 9. And then the height of the container is 8.75 E negative 9 as well. So the volume varies linearly with the width. So realize that normally volume is, if you want to find the volume of something, you take the width and then you times by the height and then you times by the depth. Well, all the depth and the height are just going to be constant in the simulation. So all that happens is if we change this width, if we move this in and out, then we're changing the volume by changing the width. Light particles have a mass of 4 atomic mass units, and the heavy particles have 28. We're not going to worry too much about these. We're just going to use the heavy particles. You can, if you wanted to, you can mix some light particles in there, but that's beyond the scope of what we're trying to do here. The pressure gauge will display 0 pressure until the first particle wall collision. So we don't have to worry about that because we've got particles in here already. Moving the container wall will not do any work on or by the system. When the container wall is grabbed, the simulation will pause. Upon release, the particles will instantaneously distribute in the container and their speeds will remain unchanged. So you can see that when I grab this, it stops everything. And I bring it in and let it go. That's not realistic, right? Because in real life, if I were to, pull this in, if I were to pull in the edge of the container, like pull it, I guess it's, wait, which way is it? This way, this way. If I pull it in this way, then I'd actually be exerting a force on those particles. I'd be doing work on them, and then that would actually add energy to the system. Well, what this is doing is just we're doing changes in volume that are not adding or removing energy from the system. And so that's just what that is telling us. So as soon as you grab this, it's an instantaneous change, so it's not doing any work or removing any work from the system. When the system temperature is below half a Kelvin, display will show 0. Particle motion will eventually stop, but the container is cooled further. We're not going to worry about doing that. All right, here are the directions for this assignment. You're to conduct 4 different investigations of an ideal gas. So we want to look at how do changes in volume affect pressure? How do changes in volume affect temperature? How do changes in pressure affect temperature? And how do changes in the number of particles affect the volume? So these are the relationships we want to uncover, and we're going to do it experimentally by changing these quantities within the simulation. So you can notice that I can change the volume here, and I can see how does that affect the pressure. So if I decrease the volume, it increases the pressure. If I increase the volume, it decreases the pressure. So that's the first relationship. Volume and pressure have a direct proportionality. So increasing one decreases the other. We could also do volume and temperature. And so that's what you're going to have to do over here is hold constant. So if I change the volume and I want the temperature to change, then that means that I'm going to need to, if I say hold constant temperature, then watch what happens when I change the volume. So you can see that the temperature is staying the same. If I hold constant pressure with, it says volume can, what am I trying to say? The volume is not variable now. So see how when I clicked on this, the volume adjuster went away. So if I click on this one, I think it's a little confusing, but it's going to hold the pressure constant. And so what I can do now is I can add heat to it and it will increase the volume. Or I can remove heat from the system and it'll decrease the volume. So the pressure is being held constant, but the volume is allowed to change. So the pressure is held constant, but the volume is allowed to change. So when we supply heat, it expands, and when we remove heat, it contracts. And the last one here, if I click this, pressure is held constant. You'll notice that my controls for supplying heat have gone away. And so now when I move this out and in, we're still keeping the pressure constant, but now the temperature is changing. And you'll notice that it does do a quick little animation showing you what it had to do in order to keep the temperature constant. So this one is holding the pressure constant, allowing you to change the volume by changing the temperature. And then this one is holding the temperature constant, allowing you to change holding the pressure constant, allowing you to change the temperature by changing the volume. Okay, you could also look at there's got these other options in here, but we don't need to worry about any of those. Okay, then that's the basic setup. The goal of each experiment is to determine the mathematical relationship between the two quantities. This means designing an experiment to vary one of these quantities, that's your independent variable, the one that you're changing, and then measuring the resulting change in the other quantity, being your dependent variable. All other variables which can affect the dependent variable must be held constant. Note, you can hold variables constant in the simulation by using the hold constant menu. The simulation allows you to directly control the following variables. So we can change the container width, we can supply heat, and we can change the number of particles. So that's the only controls that we have access to. So we can change, if I click on hold nothing, do nothing. Okay, I can change the volume, I can add or remove heat, and I can add or remove particles. For each investigation, you will collect, process, and analyze data using a spreadsheet. It is highly recommended to use Microsoft Excel for this activity. For each experiment, create a properly formatted raw data table, process data table, and scatter plot of the quantities. You must collect a minimum of 5 data points for each experiment. Do not forget to estimate the uncertainty in every measurement. And you know what? I decided not to worry about this. We'll do uncertainties in the actual experiment. For today, it's just kind of it's beyond the scope. Like if we were doing this in class, I would have made you guys do uncertainties. But as an online assignment, I think it's just probably beyond what you need to do. We'll worry about that when we do the actual experiment next week. Okay, investigations. Report the results of each of your investigations. First, give a basic description of your experimental methodology. So tell me like what you did and like your thinking behind it, why you did what you did, and what you did. And then provide a raw data table, a process data table, and a scatter plot of the experimental quantities. So the thing you'll notice is like the things that you change are not directly the variables. So when you change the width, you're not actually directly changing the volume. Like you're changing the width, which is causing a change in the volume. So these are the raw quantities. Like these are the things that we're going to be able to adjust. And then you're going to have to process that data to then determine what the actual quantities themselves are. So we're going to want raw data table, process data table, scatter plot, and then finally write a conclusion that states the relationship that you've discovered. All right, so we're going to do the first one as an example, volume and pressure, and then you will do the remaining 3 on your own. Okay, let's start. So I got the hiccups. Let me grab some water real quick. Man. All right, so we already kind of played around with this a little bit. Like we already know that if I change the volume, that it will inversely change the pressure. So if I decrease the volume, it'll increase the pressure. And so we already saw that just anecdotally here. So what I want to do is basically create a starting point. So I'm at 15 nanometers. So I'm going to say, all right, what I'm going to do is I'm going to be changing the width. So that's going to be my independent variable. And now the width is in units of nanometers. Those are the nanometers right there. Remember, this is my raw data. So I'll label that raw data. All right, so I'm going to first look at changing the width. And then I'm not going to worry about uncertainties, like I said before. And then what's the thing that we're measuring that changes in response? We're directly measuring the pressure. So pressure, and the unit of pressure is displayed in kilopascals. If I move this over. All right, so we've got the kilopascals here, and then we've got the nanometers down here. So we make changes in the volume, and that will make changes in the pressure. Okay, so the first thing you always want to do is figure out what do you want to increment your data at. So I can see that the largest I can do is 15, and then the smallest I can do is 5. And so we want to have at least 5 data points. So incrementing off there, we want to go the full span. So we want to go from the minimum to the maximum value. And so we just have to think what should we incrementally go by to go from 5 up to and then ending at 15 and to get 5 data points. So we can just try a few things like we can say, hey, what if we do by 10s or by 5s? So it'd be 10 and then it'd be 15. Well, that only give me 3 data points. So that's not going to be good. Let's try incrementing by 3. So that would be 8 and then 12 and then 15. Okay, well, that only gives me 4 data points. So let's try incrementing by 2. So it'd be 7, and then 9, and then 11, and then 13, and then 15. Well, it looks like that's giving me extra data but you know, I'll just do it with that many. You know, you don't have to have 5. Like we can do as many as we want, but I think I'm going to do 6 just because it looks nicer with these increments here. You know, all you needed is 5. If you wanted to cut off that 15, that's fine, but realize that having the 15 there is going to be nice. Having the 15 there will be nice because it gives us a wider spread of data. And you always want to have, for reliability in your experiment, you want to have as maximum a spread as possible to sort of help you identify those relationships. Because if you look at too narrow of a range, a relationship that would normally look linear might actually end up what am I trying to say? When you zoom in, something that looks linear might actually, when you zoom out, actually be like more quadratic or exponential. So you always want to make sure you have a wide enough range, as maximum range as possible when you collect data in an experiment. Okay, let's start. So I'm going to set this thing to 5, and then I'm going to look at what the pressure is. So I got 5721, 5721. And then I'm going to increment out to 7. And you want to try to go as close as you can to 7. There we go. 7.0 is what I'm looking for. Now I've got 4097. I'm going to go out to 9. And I've got 3179. So you could see here, if I hadn't turned off the noise, you'd be looking at this and you'd be like, all right, here we go. So I'm at 9 nanometers. Okay, what is the pressure? What? It's fluctuating. What do I do? Well, then you'd have to, estimate the uncertainty. You try to pick like the average value that you see and then try to estimate plus or minus. We're not going to do that. So that's why we're sort of hacking the simulator here and turning off the noise so we get that exact 3179. Okay, and then I'm going to go out to 11, there, 11 nanometers. I'm at 2592. I'm going to go to 13, 2207, and then to 15, 1907. So there's my raw data. Okay, now what we want is we want a graph of volume and pressure. So we want to graph the volume and the pressure. Now, the thing that we're changing, which is the volume is what we're controlling, that always needs to be your horizontal axis. So the dependent variable is always your horizontal axis. Then your vertical axis is your dependent variable. So you got the dependent variable here, the thing that you're measuring in response to changing this thing. So your independent variable on the horizontal and your dependent variable on the vertical. So in this case, the independent variable ends up being the volume, and we're going to want to express that in the units of meters. And then the dependent variable is the pressure, and we're going to do that in pascals. So what I'm doing now is I'm converting these guys over to their standard units. So instead of nanometers, I'm switching over to meters. And instead of kilopascals, I'm switching over to pascals. So that's why this is the processed data table, because I'm going to process these values up here and change them to be the correct units. So let's do the pressure first. So if these are 1,000 pascals and I want to turn it into pascals, then I just have to multiply these guys by 1,000. So I'm just going to carry that down to the bottom. I went a little bit too far there. That's fine. Okay, so now these are listed in pascals. Great. I feel like I should probably zoom this in a bit. Okay, then the next processing we want to do is convert from this width into a volume. And so remember that volume is width times height times depth. So looking up here, here's our depth, and then here's our height. And so we need to find the volume is by multiplying all of those together. So the first thing we'll do is probably think, all right, let's convert everything into meters, and the volume is just multiplying all that together. So if we convert into meters and realize that this 5 actually needs to be times 10 to the negative 9. So what we'll do when we calculate the volume is we're going to take this depth times this height times this number times 10 to the negative 9. And then that'll give us our volume in cubic meters. So we're going to have, this is going to be meters times this in meters. So realize that when we did that, so I'll put this in parentheses here, when we did this part, so B2, this number, already in meters, times this number, already in meters, times this number, but it's in nanometers, so we multiply it by 10 to the negative 9 to get those nanometers into meters, since nano is 10 to the negative 9. So now our volume is there. But now, if we try to copy this formula down, bad things happen. Oh, and the reason why is because we were also, the things that we referenced up here also got dragged down. So the way to fix that is in the spreadsheet, you have to create what's called a fixed reference. So I'm going to double click on this cell to open up my equation again. And then I'm going to click on the function key F4 here. And when you click on your B3 here, when I click and hit F4, it will put these dollar signs in front of it. Now, you could also, I'll undo this. You could also just manually put those dollar signs in there. So the dollar signs say, hey, when you copy this formula, when you like try to autofill with this formula, don't try to change the cell. Leave it the same. And so when I put a dollar sign in front of the B, it's going to make sure that when I drag it down, it always stays in this column B. And putting a dollar sign, oops, and then putting a dollar sign in front of the 3 says, hey, when I drag this down, instead of making it come down off of 3, keep it on 3. And so that's what those dollar signs do, is they lock it so that that cell never changes. And since those values are constant and they're fixed throughout the experiment, we want to use these fixed cell references whenever we want to pull those numbers. If you wanted to do it, you could also just manually type the numbers in there, like just wrote for E negative, but this is just an easier way of doing it. Okay, so now if I double click here, bloop, it'll automatically fill in the remainder of our volumes. And so now we're done. The data is processed. Now we just need to create a scatter plot. So we've got our raw data, we've got our process data. Now we just need a scatter plot. So we're going to grab our quantities here. We're going to click insert. We're going to do a scatter plot. There's our scatter plot. What I'm going to do is just make this larger. Okay, so here's my scatter plot. We can notice right away that it's not a linear relationship between these quantities. We can see that downward trend as one quantity is increasing, the other quantity is decreasing. So we're very happy that we can visualize that. What we want to do is go to chart design, and we always love choosing format 3. It's going to try to do a linear fit when you do the chart design quick layout number 3. It's going to always try to do a linear fit there. So I'm just going to grab that trend line and delete it because we don't want that trend line. I'm also going to delete the series label because we only have one data series on our graph. There we go. Okay, so now to find the axis title. So remember that I'm going to click this title here, click it, and I'm going to go up to the formula bar. I'm going to press equals, and I'm going to say this is my vertical, so that's the pressure. And then down here, this is my horizontal, so that's the volume. And since we labeled the quantities and their units over here, it's automatically labeling on our graph. You might want to say, hey, these numbers are kind of gross, like how big they are. So we can actually double click there and we can say down here for the labels or the number, you can say, show it to me in scientific notation and do 1 decimal place. And so that way it will, I guess it didn't really make it look nicer, but it's a little bit better than it was before. And then this part down here is already in scientific notation. Everything looks great. So we are good. That's it. I don't want you guys to do any trend lines or anything like that. I just want you to see that it's not linear, so that the curve is trending. This is an inverse graph. This is what inverse looks like. It's 1 over x. It's a graph of 1 over x. I guess I could show you guys if we go to Desmos, the best website in the world, and I make a graph of y equals 1 over x. You can see that it looks just like that. There you go. That's the inverse relationship. There we go. Okay, so now we are basically done. We just have to copy our raw data. So I'm going to grab this and then I'm hitting Command C. And then I go into my here and then paste it in. That's my raw data. I also want to paste in my process data. So I'm going to grab it, Command C. Oops. And paste that in. Bloop. Oh, this is looking really gross. I'm not liking how this is formatting, so I'm going to undo this. All right, so what I think I'm going to do instead is I'm going to rearrange things inside my spreadsheet just so that I can output it and have it look a little bit nicer. So I'm going to increase the width of these columns. I need to make sure these guys are centered. This is just aesthetics. Like you don't have to do these. I just think it looks nicer when I do this. Okay, then I'm going to give a white fill on everything so it doesn't look gross. I'm going to insert another column here, and now I'm going to take a screenshot. So Command Control Shift 4. I don't know. On Windows, it's just Windows Shift S, but I just took a screenshot there, and then I'm going to go back to here and just paste it in. And I think that looks beautiful. It looks a lot nicer than the other part did. There we go. There's raw data. I'm just checking to make sure everything looks good. Width, nanometers. Yep, everything looks great. And then I'm going to grab this. Now remember on Mac, you can right click here and you can save this as an image. You cannot do that on Windows. So unfortunately, I am going to have to take a screenshot, make sure that the graph is not selected because you don't want these weird like selection graphical user interface items. So click off the graph and then screenshot it. Obviously, it's better if you just save it as an image, which is what you guys are going to want to do on your Macs. Paste it in there. Okay, there we go. There's my graph. Okay, it looks fine. If you don't like the way this looks, because it does kind of look gross, like you can, if you want to, you could change the appearance of these things. So I'll go over here and change my marker. to use a smaller size dot. I will also make there be a solid fill of black. Black looks better. And you can see what happened there was I only selected the one dot instead of all of them. So let me try that one more time. I'm going to click. Now they're all selected. So I'm going to do what I just did to that first one over again. So built in, size 3, solid fill, black, no border. There we go. And then that, I just think that makes it look a little bit cleaner, a little bit nicer. Now, if you did want to add a trend line, I said you didn't need to, but if you did want to, you can click add a trend line, and you can click on these buttons to see which one looks like the best fit. But you'll notice that it looks like power is the best fit. There we go. So that's my power fit. If you want to, you can, forecast it backwards, forecast it forward. It's going to give you this. Oh, geez, I have to actually choose nicer values there, don't I? So if I want to go forward, let's do 1e negative 25 forward. And then let's do 1e negative 25 backwards. So now we can see that curve a little bit better. So our data is fitting this inverse curve there. You can make the case that, I don't like this. There's too much space up here. You go, all right, well, let's just cut this off at 8. So I'll go in here and say, all right, the maximum, just go to, instead of 1.6 E7, let's go to 8 E6. And so now my data is more well represented there. Likewise over here, looks like we want to stop at 6E25. So I'll go 6E negative 25. And so now my data is better represented on this graph. You can see the trend anyway. That's the plan. So like I said, you don't have to do this. Like the graph that I pasted in here is fine. But if you want to make it look even nicer, like if you care about your presentation, then I would recommend doing those changes that I just showed you there. I just noticed something disgusting. I do not want this. I want this to be at 0. So I want the minimum to be 0. I don't want to go into the negatives. There. Okay, now I'm good. So now I'm going to grab this. And then I'll paste it in here. All right, now I'm happy with this graph. It looks fantastic. What did I do? There we go. The zoom is good now. Okay. Awesome. Let's keep this at 100. Okay, so now we've got, let's look back at the direction. So it says provide a raw data table, check. Provide a process data table, check. Scatter plot of the experimental quantities. And you might be thinking, oh, I'm done, yay, but actually we didn't do 2 things. We need to give a methodology. So we'll highlight this. And then we also need to write a conclusion which states the relationship between the quantities and to explain our reasoning. All right, so first we'll talk about the methodology. So the methodology, width, container width was adjusted from its minimum value of 5 nanometers to its maximum value of 15 nanometers. The pressure, it was adjusted in increments of 2 nanometers from its minimum value of 5 nanometers up to its max value of 15 nanometers. The pressure was recorded at each of these width intervals. There we go. That's it. That's a description of what we did. The methodology is just what you did. It was your thinking and your reasoning behind the experiment. So the reason we wanted to do from 5 to 15 was we wanted as large a spread as possible. Okay, now we need the conclusion. So our conclusion is that pressure is inversely proportional to volume. This can be seen from the graph. This is our reasoning. It says explain our reasoning. This can be seen from the graph since it makes the same shape as a graph of y equals 1 over x, or x to the negative 1 power. So superscript negative superscript 1. Okay, there we go. And then I'm just going to be super awesome. I'm going to go into Microsoft Word and I'm going to open up the equation editor and I'm going to type pressure equals 1 over volume. Like that. I'm going to zoom in on it. Whoops. Where did it go? No, what happened? Ah, there it is. Okay, I found it. And I'm going to screen grab this. Oh, not equals. I screwed up. Prop to proportional to. There we go. Oh my gosh, I just lost it again. Okay, there. So the reason I'm doing this in Word is because I think it looks nicer than Google Docs. Google Docs has a fairly bad equation editor, and I just think this looks way, 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 way better. There we go, and that's it. That's my conclusion. I'll make this in bold just because it looks nicer, and then do that in bold like that. There we go. So that's the first experiment. And so all that you guys would do is you would just go and do the second one, the third one, and the fourth one. I'll just briefly show you how to do those because it can be a little bit confusing. So for this one, we want to see how the volume and the temperature are related. And so remember that means holding everything else constant. So we need to make sure the pressure is constant, but we want the volume to change. So you're going to need to do this setting right here. Make sure you still have the 500 particles in there. And now you want to think about, well, what are my, extreme values? So if we're looking at, where were we? Okay, looking at here. Okay, we're trying to see how the volume and the temperature relate. So what we would do is we'd think, all right, well then I'm going to need to knock that volume down to the slowest, to like the lowest possible that it can go. So I'm going to lower this down, lower it down, lower it down until it gets down to that 5 nanometers again. Okay, there it is. It says, whoops, pressure cannot be held constant, volume would be too small. Okay, so now that we've reached down to that lowest volume, we can record that temperature, and then we can just start to increase in steady increments from that. Oops, I have this messed up. So pressure, boom. Okay. So now we're here at our starting point, and now I'm just going to increase this, and then you're going to decide what temperature increments to do. So you might want to actually go all the way to the end and then see what happens when it maxes out. Boom. And then hopefully it doesn't reset it. It looks like whenever you reach those maximums, it's going to reset you. So be careful about that. But anyway, you can see that it's with the 15 nanometer width, we're at 217 Kelvin. And then I would have to drop this down. Nope. Keep the volume variable. Okay, here we go. And so that's, you just want to get your extreme values that way. So just be careful because when you hit the edge, so let's watch it one more time. So we're looking at the temperature, 60, 59, 59. Oops. Okay. Then I got my 5 in the 59. That didn't change, but the setting over here did change. So make sure you put it back to pressure with a very constant pressure, variable volume. So that's for this one. For number 3, we want to change the pressure from a change in the temperature. So that means we need to hold the volume constant. And so now as I increase this, as I raise the temperature, you can see what it's doing to the pressure. So do a similar thing here, push it as far as you can to get your highest value, and then push it as low as you can to get your lowest value. So you'll notice that as I continue to heat this up and the particles start to move faster and faster and faster and gain more and more, oh, the lid pops off. So be careful because if that happens, if you pop the lid, if you pop off, then you're going to need to go back down here and remember to set yourself back. Whoa! To set yourself back to 500 particles. If you forget to return the particles to 500, all of your data will be corrupted and you'll have to start the experiment over again. You'll know that that happened if one of these points is like, bloop, like way off, and then every point after that's way off. Like if it was coming down, if I see this nice trend and all of a sudden right here, this point was up here, and the next point and so on, then you know that you messed up and you got to go back and redo that data. So make sure that that particles is always at 500. Okay, for the last experiment, how does the number of particles affect the volume? So for that, we want to, what do we want to keep pressure? What do we want to keep constant for that? Particles and volume. Let's see. So we want, let's see, this one. Can I? This is nuts. All right, now I'm going to start to decrease the number of particles. Pressure cannot be held constant. Volume would be too small. Let's see, why is the? Oh, I see. I got this. I'm all messed up here. Is this one even going to work? I thought I had this working earlier. Yeah, this one's doing it. Okay, so I want number of particles. Oh, number of particles and volume. I guess we need to change that. That's my bad. It's looking like you need number of particles and pressure, not volume. It looks like there's no way to do. Maybe I'm speaking too soon. It feels like there's no way to do it where you're holding. Let me try one more time. So if I've got number of particles and pressure, I want to hold. That means I'm going to keep the temperature. The temperature and the pressure are going to be constant. So let's see if I can hold the temperature and the pressure constant so that when I add and remove particles, it's changing the volume only. Okay, let's see if I do nothing and see what happens. Nope, that's increasing the pressure. Okay, so let's reset that back. Okay, so let's try holding pressure constant, allowing the volume to change. Let's try that one. There we go. That's what I want. Yeah, okay, okay, there, that's what it is. Okay, cool. So, uh, just to remind what we did. So for this last one, number of particles and volume, we need constant temperature and constant pressure. So looking back here, you can see that as I reduce the particles in here, it didn't hold it constant, did I? Let me go back up. So I'm gonna max this out, return lid. Can I max it out? Let me cool it down. Okay, now I'm gonna max it out. Okay, so I maxed out here. There's one particle floating over there. Maybe we should reset. Okay, so let's reset. I'm going to pump this up all the way to 1,000. I'm going to stretch this all the way out to full. This is awesome. Pew, 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 pew. Okay. Then what we want is we want the pressure to be constant, allowing the volume to change. And then we'll let this thing kind of reach an equilibrium, like stabilize. We'll know that it's stabilized when the pressure is no longer fluctuating or the temperature. Okay, so now we got constant temperature, we got constant pressure. Now I'm just going to go bloop and knock this down, and then we can see that the width is changing. So I'm incrementing by 50 particles. Every 50 particles, you can see that the volume is changing. And so that's how you would do the last experiment. So it says here number of particles and volume. Okay, if you guys have any questions, if you need anything, find me on Discord or send me a private comment on this assignment inside Google Classroom. That's it for today. I hope you guys have fun. Don't stress yourself out too much about this. You just follow the example that I gave you here for all the other ones. When you're done, you're going to have an expression, a mathematical expression for each one. And in the next lesson, we're going to put those all together into an equation. It's called the ideal gas equation. All right, have a great day, guys. I'll see you later. Bye.